Alright, so for our next lesson, what we're going to look at today is electric potential energy. And what I want to do is relate electric potential energy to gravitational potential energy that we dealt with before. So let's put some gravitational potential energy there. Now when we're talking about having a mass above the ground, it has a certain amount of gravitational potential energy, easy for me to say. Now if we increase that distance and move the mass up, our gravitational potential energy is actually going to increase. And so we found the work that it took to move that mass upwards is our force times our distance, which again represents our change in gravitational potential energy. And we can also say that our change in gravitational potential energy, because we're talking about this force, which is the force of gravity that we're counteracting, and the force, or the formula for the force of gravity is m, the mass, times g, and again our distance, or our change in distance I should say, is delta d. Now here's the important thing, is that as our distance, the change in distance, increases, so does our change in gravitational potential energy. It goes up, right? We pull that object further from the Earth. The further from the Earth we pull it, it's going to have more gravitational potential energy. But now what we're going to look at is electric potential energy, which is a little bit trickier. Now I have the ground in this case, which is a positively charged plate, and I have my positive charge there. Alright, and so our electric field always moves out, upwards. And so if I move this positive charge, again, farther away, just like my mass was moved farther away from the ground, I'm going to move this positive charge farther from the positive plate. Alright, and the work that I'm putting in to do that is I have F times d again, but I'm using the electric force. And again, I'll put my distance, or my change in distance that I move it. Alright, now, but here's the trick of this one, and this is why it's a little bit tricky, is that if I'm moving this positive charge away from the positive plate, I'm actually losing electric potential energy, because two positives repel each other, and pushing them together builds up electric potential energy because it's like a spring. And so if I move them away from each other, that spring now is, well, it's being released, or it is less tension in there. And so the trick here is that as delta d, our distance, increases, it means, as I said, a decrease in our electric potential energy. And again, it's because it is now less repulsed. Right? When you take two charges and you push them together, the repulsion builds up. But as you move them apart, the repulsion and that energy decreases. And so, therefore, this work here, which again is our change in electric potential energy, we have delta EE, again our change in electric potential energy, is equal to, again I'm going to put F, I'm going to leave a space here, Fe times delta D. But because the opposite thing is happening, as we increase our delta D, we actually get a decrease in electric potential energy. And to show that things are the opposite, I'm going to put a minus sign there. Alright, now, we also had our formula from yesterday that our electric force, Fe, is equal to Q times epsilon. And so if I make that substitution into our formula, we're going to have a new formula in which we've got delta E is equal to, let's see here, negative Q epsilon, So there's that Fe, and again times our delta D. So there's another formula for us to use. Now again, here's the problem with electric potential energy, is that there, with all charges, there's two cases. And that's a bit of a problem. So there is two cases. All right, now I'm just going to draw a little graph here of what we've got. There we go, hopefully that helps out. And again, on the left on our y-axis, we're going to look at the electric potential energy, where you have positive, we'll say, electric potential energy, and we have negative electric potential energy. And so what can happen is if you have a positive charge up here, the farther you move it away, the less energy you have. The closer you move it, again, pushing that spring together, you're building up a lot of positive energy here. But again, as you move it farther apart, your energy dwindles. And so again, as D, your distance, or I should push delta D, increases, your electric potential energy actually decreases. I'll put delta again because it's the change. But we don't only just have positive charges, we also have negative charges. And negative charges, again, act like a spring, where we have a positive and we have a negative. And as you pull them apart, because they're attracted to each other, it's again like a spring, but it's a spring where you're expanding that spring, extending it. And so the farther you pull that negative away, the more energy that's built up. And so if we have a negative charge in this spot and we move it farther away, we're going to have more energy. But to show that, here's what we're going to do. I'm going to draw the graph just like this. And so what's happening is, to show this difference that can happen, is as our negative charge is pulled farther away, we actually, again, increase our electric potential energy. But to show this on a graph and to make it make sense mathematically, it's going to be less negative. And so at the beginning, when you have the positive and negative together, because that's what they want, they just want to be together, there's not a lot of energy built up there. Or in this case, we can say we have a lot of negative energy, right? So you could say it's something like negative 500, but as you move them farther apart, you could say it's like negative 200. So even though they're both negative, the energy level has increased, right? It has increased. It just happens to be less negative in terms of mathematics. Now, if, this is coming back to our formula here, if, which it is, delta E, our change in electric potential energy, that's the key with delta, it means change in math and science, it's something we're going to get to. And we have our negative Fe times delta D. Really what we're concerned about is that we're going to assume that these charges, that our distance is equal to 0, so we'll put di, our initial distance is 0. Then we can get rid of the change and we just have EE is equal to negative Fe times D. Now the reason I want that is I'm going to make a substitution, and so, because there is two cases. And the substitution I want to make is that our electric potential energy is equal to Fe times D. I'm not worried about the negative sign, and I'm going to explain why I'm not worried about the negative sign right now. Is that I'm going to sub in Fe, a formula we had the class before. And the formula for Fe was the electric force, K, the constant, times Q1 times Q2, divided by D squared, and then multiplied. So again, that's our formula for the electric force, Coulomb's law. All right, and then we times it by this D. Now, what's going to happen here is that we have a D squared down here and we have a D here, and so that D will cancel out one of these D's. And so our formula for electric potential energy get rid of that D, and then I only need to get rid of one here, is that we have our electric potential energy is equal to K times Q1 times Q2 divided by D. And the reason I got rid of the negative sign, because again, there is two cases, but when you have two Q's, Q1 and Q2 are both positive, then your electric potential energy will be defined as positive, right? But if one of our charges, one's positive and the other is negative, then we're going to have some negative electric potential energy. But again, what we're concerned about is the change, right? With the positives, two positive charges, we move a positive away from the positive plate. Again, the energy decreases. If we move a negative charge, say this was a negative, I can do that right there, move this negative charge away from the positive plate, again, we're going to gain energy. Because again, it's like a spring, they're pulling them apart. Now again, like I said, we're worried about the change, which gets me to my next point, which is the conservation of electric charges. All right, conservation of energy of electric charges. Where again, the change in our electric potential energy plus the change in our kinetic energy, the change, is equal to zero. And here's what I mean by that, is that we get a situation, and again, because there is always two cases with electric charges, because we could have a positive and a positive, or a positive and a negative. And the first case is, again, we have our positive plate down here. All right, so let's put that there. And we're going to take a positive charge, and it's going to move away. All right, and so what's going to happen is that we're going to have two things here we're going to look at, our change in electric potential energy and also our change in kinetic energy. Now again, when these two charges are pushed, because they're both positives, and like charges repel each other, you push them together, that energy builds up, but then if you let them, it's like you let one go, you let this one go, it's going to move off. And so because that tension between these two positive, the positive plate and the positive charge, are now not as great, we have a loss of electric potential energy. But what's happening is, as we build these charges up, we let it go, it's going to take off. It's going to be speeding up. And so we have an increase in kinetic energy. All right, so that's moving a positive charge away from a positive plate. But like I said, there is another situation here. Is that when we have, again, a positive plate here, let's draw that in there, nice positive plate. Let's put some plus signs. Okay, now I've got that negative charge. Now again, a positive and negative are attracted to each other. All right, so what I'm going to do is move this negative charge, or let it move, or move it away from the positive plate. All right, and so again, if I look at both the electric potential energy and the kinetic energy, what's happening this time? Well, the negative charge is being moved away. And it's because a positive and a negative are attracted to each other. As we pull them away, we're increasing our electric potential energy. But what's happening is, you've got to think as they want to be together, and as you're pulling them away, or you can almost look at it that it's being thrown, well, they're being attracted, and so what's happening is this charge is actually slowing down. If you look at it in motion. All right, so this negative charge is shooting this way, it's being thrown this way, if you will, but because it's attracted to the positive plate, we're building up that electric potential energy, but at the same time, this charge would be slowing down, which means we now have a decrease in kinetic energy. And now what we're going to look at is a couple of examples of how this works.